Hello everyone, I'm Chanjong Park. I'm working in Samsung Research as an AI engineer. In this talk, I'm going to present collaborative learning with pseudo labels for robust classification in the presence of noisy labels. Noisy labels are converted labels to other label category, and these can often exist in real-world datasets. Because data labels are written by humans, and this process is error-prone. These noisy labels induce the deep neural network to be learned towards wrong targets, and eventually they deteriorate the generalization performance of the networks like presented on the right figure. So there have been many previous works to overcome this problem, and we also propose a method for learning with noisy labels, named collaborative learning with pseudo labels. There are two main features on our proposed method. First, two models which have different initial weights are trained simultaneously. They divide mini-batch inputs into small loss and large loss instances. This makes use of the trait that deep neural network learns the correct labels first on the training with noisy labels. And the two models are cross-trained with exchanging these instances. This process makes two models keep diversity and prevent overfitting to hard noisy samples, misclassified ones. Therefore, this method effectively filters the noisy labeled samples. But this approach is supposed to discard a certain amount of training data, so they suffer data inefficiency problem from it. To compensate this problem, we focus on the large loss instances, which have noisy labels. We think that their labels are wrong, but their image data can still be useful for training. So we propose a method using pseudo labels instead of noisy labels. The pseudo labels are predicted result of the models, and the models predict and assign pseudo labels by themselves based on the knowledge they have learned about small loss instances. So next is the overall training process is as follows. We described this in 3 steps. The first step is to separate the labels. The two models get the same mini batch and calculate the loss with their respective weights. Then they separate the mini batch into small loss and large loss instances. And next, the model generates pseudo labels. We get the prediction result of models and replace the noisy labels with them. But we don't use all these generated pseudo labels directly. To select the potentially more accurate pseudo labels, we set a certainty threshold and choose only instances with less loss values than the threshold. The last step is to train the models with selected instances. At this stage, the models exchange their two types of instances. Small loss instances without any post-processing and large loss instances with pseudo labels. Each network receives instances from each other and updates their weights using them. And the next page is how can we trust the pseudo labels? We present how we get reliable pseudo labels in this page. These two graphs are histograms of two types of labels. They show that the noise labels and pseudo labels have similar distributions based on their losses. The network has trained mainly on the small loss instances, and this is well reflected in the predictions. Therefore, the correct pseudo labels are also clustered to the small loss side. So we define the certainty threshold and select only pseudo labels whose loss values are less than the threshold. And next, we will talk about the effectiveness of pseudo labels. The graph shows the changes of label category distribution during the training. Since cipher 10 with symmetric 50% noise is used, the correct and incorrect data are half and half at the first approach. And then, as training proceeds, we gradually reduce the ratio of small loss instances A and B to 50%. In this period, we can see that the model identifies small loss instances with many correct labels, A. But these are only 50% of entire training data. So for the rest, we can see that the model generates pseudo labels C and D. And the models correctly recovered about 80% of pseudo labels as shown by C. As a result, the model can be trained using almost entire training data with 83% of correct labels. This is sum of A and C. Now let's move on to the experiments. We can see the most accuracies of algorithms show fast increase first, then decrease after reaching maximum. Decreasing accuracy means that the network starts to memorize the noise labels. But our approach is less affected by this phenomenon and shows the highest maximal accuracy and the highest average accuracy of the last 10 approach. Especially on tiny ImageNet dataset, test accuracy is showing an upward trend until the end of training. For conclusion, at first, we propose a method for end-to-end learning on the data with noise labels. Our method trains two models simultaneously and separate correct and noise labels. Then it replaces noise labels to pseudo labels and leverage them for training. Finally, this allows training deep neural networks robustly on data with noise labels while keeping data efficiency. So this is end of my presentation, and thank you for your watching.